Alright, well, let's continue recording this. I'm sorry if the sound quality is pretty bad. Again, there's RoboNerd shouting to my left and some sort of exciting movie happening to my right, so this is the quietest place I could find. Alright, so the next section is circular motion, which means it's torque, universal gravitation, and centripetal force. The first one is torque. It's a seesaw problem. These are pretty simple. If you look on the formula sheet, it gives you the formula that says F1 D1 equals F2 D2. And so at first glance, this looks really easy because we have F1 is 14.5 newtons, F2 is 22 newtons, and at first glance, it's like, oh, well, they gave you D1, so you just have to find D2. They did not give you D1. They are trying to trick you. Look at what they're telling you. This is another time that a picture is pretty useful. They tell you that the whole board is 25 meters long, and that you are 3.2 meters from the end. No, neither of those is what you care about, because what we care about is the distance from the object to the center. Again, neither of the numbers they gave us is that. So what we have to do, each side is going to be 12.5 long. So like here's our thing again. This side is 12.5 meters, and this side is 12.5 meters. If we know that we're 3.2 from the edge, then we are 12.5 minus 3.2 from the center. So our distance from the center is actually sorry, RoboNerd interruption. Anyway, so once we get to this point, once we have our D1, then it is pretty simple. F1 D1 equals F2 D2. So 14.5 times 9.3 equals 22 times D2. 14.5 times 9.3 is 134.85 divided by 22. That gives us that D2 is 6.13 meters from the center. Yay! Alright, this next one is a gravitational force problem. The formula for that looks like this. F sub g equals g m1 m2 over d squared. The big keys to this problem are just remembering really what this is. So this is the gravitational constant. It's given, it's on the formula sheet. It's 6.67 times 10 to the negative 11th. You are not required to memorize it, but you have to remember to use it. And then, of course, our masses, m1 is 42, m2 is 55, and the distance apart is 2.5. So, 6.67 times 10 to the negative 11th times 42 times 5 all over 2.5 squared. This is one where you just have to be careful that you plug it into your calculator correctly. If you're using my dumb class calculators, just be super careful. Since they don't have the EE button, you just have to be really careful when you're plugging things in. There's lots of parentheses. No such thing as too much parentheses. I am getting that the gravitational force between these two objects would be 2.5 times 10 to the negative 8th newtons, which makes sense because they are not very heavy and the gravitational force between them would not be very strong at all. As far as units go, sorry about that. DJ Biscuit says hi. 6th period knows who that is. The rest of you don't have the pleasure. Alright, number 13 is a centripetal force problem. The two equations for centripetal force or centripetal motion. Centripetal force is just mv squared over r, and centripetal acceleration is just v squared over r. So this tells us a car is racing on a fast track. It goes 32 meters per second, so that's our v is 32. Which has a radius of 56 meters, so r is 56. What is the car's centripetal acceleration? So centripetal acceleration, v squared over r, 32 squared divided by 56. Sorry, calculator struggles. And I'm getting that AC is 18.28 meters per second squared. If it has a mass of 2,150 kilograms, FC is going to be mv squared over r. It's going to be a pretty big number, 2150, 32 squared divided by 56. 2150, 32 squared divided by 56. It is very large. It is 39,314.28 newtons. I think Dante/DJ Biscuit interrupted me when I was saying this, but I will be taking off for units, so make sure you include those. Alright, we're in the home stretch now, guys. Work, power, energy, and simple machines. You should be great at this. This was the best test grades we had all year. A 3.5 kilogram ball rests on top of a table. The table is 1.4 meters tall. What gravitational potential energy does it have? Well, potential energy is mgh. M here is 3.5. H is 1.4. So 3.5 times 9.8 times 1.4 and I am getting that it is 48.02 joules is the potential energy. Now, the next one is the only one that requires a little bit of thought. It says how much kinetic energy is gained when the ball has fallen 0.5 meters from the top, because your gut instinct is to try to use the kinetic energy equation, but you can't. We don't know the velocity, and kinetic energy equation has velocity in it. What you have to do is you have to realize that because the total energy stays the same, that kinetic energy gained is going to be equal to potential energy lost. So we're going to use the potential energy equation again. We're going to say, alright, what's the potential energy that's lost if our 3.5 ball drops 0.5 meters? The answer is 17.15 joules. So that's the potential energy lost, and it's going to be the kinetic energy gained for part B. So then for part C, how much kinetic energy would it have just before it hits the ground? At that point, the potential energy is 0, because the height is 0. So all of this potential energy became kinetic. So there's no math required for that one at all. We just say that at that point, kinetic energy equals 40.02 joules. Then last but not least, for part D, you use the fact that kinetic energy, you're looking for velocity. What is the speed just as it reaches the ground? Well, kinetic energy is 1/2 mv squared. So if we know that the kinetic energy is 48.02, 1/2 3.5 v squared, 48.02. So I'm getting that v squared equals 27.44. Careful that you don't think you're done at that point. You have to take the square root of both sides. And I'm getting that the velocity is 5.24 meters per second. Okay, the next one is also about potential and kinetic energy. A 525 kilogram cart is rolled down a 2.7 meter hill. What is its potential energy at the top of the hill? Easy peasy. P equals mgh, where m is 525, and h is 2.7. So 525, 9.8, 2.7. 13,891.5, joules. Awesome. What is its potential energy at the bottom of the hill? Well, at the bottom of the hill, its height would be 0, so its potential energy would be 0. How fast will it be moving once it reaches the bottom of the hill? This is exactly the same as up here, guys. All of this potential energy has become kinetic, so we know that the kinetic energy is 13,891.5. We can set that equal to 1/2 mv squared. So that's 1/2 525 v squared. And we just solve for v. So 13,891.5 divided by 0.5 divided by 525. I'm getting that v squared is 52.92. Square root of both sides. And the final velocity here I'm getting is 7.27 meters per second. Alright, this last one's a little bit different. It is simple machines, so we're looking with actual mechanical advantage, ideal mechanical advantage, and efficiency. So, a package weighing 55 newtons is lifted to a height of 2 meters by pulling it up a ramp 24.4 meters long. The person is pulling the package exerts a force of 6.5 newtons. How much work did the person do? What is the AMA? What is the IMA? What is the efficiency? Alright, the big thing that we need to do, we have two forces, force input, force output, and we have two distances, distance input and distance output. We need to identify which is which. Some of them are easy. Force input should be easy. If it says exerts, that is the input force. So he exerts a force of 6.5. So that's the input force. The output force is usually the weight. So the 55 is the output force. These are a little more difficult. You really have to think about it. The output distance is how far they end up moving it. Here, the goal was to lift it the height of 2 meters. That's the output. The input is that they had to pull it up the 24.4 meter ramp. So, once we have those, things get a little simpler. To do part A, work equals force times distance. You would do the input distance and the input distance and input force, since we're looking for the work the person did. So that's 6.5, 24.4, it's not a decimal, whoops. 6.5 times 24.4, and I am getting 158.6 joules of work done by the person. Then in part B, the mechanical advantage, or AMA, the formula for AMA is F out over Fn. So here that's 55 over 6.5. So our AMA is 8.46. AMA and IMA, neither one have units because they're just ratios. IMA is switched from AMA. It's D in over D out. So that's 24.4 over 2. So IMA is 12.2. If you can't figure out which one's supposed to be in and out, remember that when you use the AMA and IMA equations, the larger numbers should always go on top. AMA and IMA should always be greater than 1. Then this should say D, it says B, but it should say D. For part D, the efficiency, there are 2 equations for efficiency. The one we want says efficiency equals AMA over IMA times 100%. So for us that's 8.46 divided by 12.2 times 100%. And I'm getting that efficiency for this is 69.3%. It should never be greater than 100, and you should be able to tell by looking at this that it's not terribly efficient. It should be able to get a ratio of 12, and it's only got a ratio. Alright guys, home stretch. We are on momentum. All 3 momentum problems are inelastic collisions, but they are each a little bit different. So this one says 2 carts with masses of 4 kilograms and 3 kilograms move towards each other on a frictionless track with speeds of 5 meters per second and 4 meters per second respectively. The carts stick together. So this is a head-on collision, which means we're going to have to do something squirrely. So let's list out what we have. We have M1 is 4, M2 is 3, V1 initial is 5, and V2 initial is 4. Now the squirrely thing that we have to do is, if you imagine 2 cars colliding, they are going in opposite speeds at the beginning. So we need to make this velocity negative to represent the fact that it's going the other direction. It wants the final speed after the collision and the direction the cars move in. So the formula for an inelastic collision, which we know it's inelastic because they stick together, is M1 V1 initial plus M2 V2 initial equals M1 plus M2 V final. So we have 4 times 5 plus 3 times negative 4 equals 4 plus 3 times VF. So 20 minus 12 equals 7. So 20 minus 12 is 8. So we have 8 equals 7 VF, which means that VF equals 1.14 meters per second. Alright, next problem. The next one says that we have, oh, sorry, wait, go back. That's part A, but part B says in what directions do the carts move after collision? The fact that we got a positive answer here means they're moving in the direction of the first cart. If we had gotten a negative number, it would mean they were moving in the direction of the second cart. Alright, now, here we have a car traveling that has a mass of 720, so M1, 720, V1 initial, 22, collides with a stationary truck of mass 1400, M2, 1400, V2 initial, 0, because it's stationary. The two interlock as a result of the collision. What is the velocity of the car-truck system? So interlock tells us that it is inelastic, so we use the same formula. M1 V1 initial plus M2 V2 initial equals M1 plus M2 V final. Now, it should make sense to you that our answer should be much smaller than 22, because this car is running into a truck, they're sticking together, they should slow down. So we're going to have 720 times 22 plus 0. This whole thing is 0 since the velocity was 0. Equals 720 plus 1400 times the final velocity. 720 times 1400, oh wow, not times, whoopsie. Okay, 720 times 22 is 15,840. 720 plus 1400 is 2,120 V final. So 15,840 divided by 2,120 gives us a final velocity of 7.47 meters per second, which is, in fact, considerably slower than the car was going to begin with, which should make sense. Number 19, we have the two carts again. Same masses, 4 and 3, M1 is 4, M2 is 3. This time, though, they're moving in the same direction. The 4 kilogram cart is initially moving at a speed of 1.2. The 3 kilogram cart is initially moving with a speed of 0.55. And they stick together. So the first thing it wants is just the momentum of them as they stick together. So the momentum has to be equal on both sides. So if we calculate their momentum before the collision, M1 V1 initial plus M2 V2 initial, that's their momentum before the collision. It's the same thing as the momentum after, since momentum is a constant, can't be created or destroyed. So 4 times 1.2 plus 3 times 0.55. We don't have to make anything negative here because they're moving in the same direction. So I'm getting 6.45. So that's their momentum. P equals 6.45 kgms, m per s. Part B then asks for the final velocity. So if we know that whole momentum equals m1 plus m2 v final, then we can just say 6.45 equals 4 plus 3 times v final. It is again going to slow down. 6.45 equals 7 VF. So VF is 0.7 0.92 meters per second. The way I worked this may seem kind of weird, but I just broke the big momentum equation down into two chunks. This was before the collision, and this was after the collision. And they have to be equal to each other because of the conservation of momentum. All right, I am